Hi all, this is my video number 31, and I think this is going to be my last video for this semester. And in this video as well, I will not give that much detail because the content of the material is actually part of the SCL, student-centered learning, where I have given the exercise for you to work on. Alright, first of all, I give some example and some formulas that I want you to try to obtain those formula, and given part of the example, try to obtain those full solution. Okay, so look at examples and formula. For the notation purpose, all this while we have written Fs as a Laplace transform, can also be written as Lf, or we can write this as F with variable s or parameter s. Yeah. Now we have seen that for Fs equal to 1, no, ft equal to 1, we know that this is Fs give you 1 over s. Now if we investigate a little bit further to look at the exponential order as well as the abscissa of convergence, so we know that f for ft is 1, the exponential order of f, this give you 0, and for the integral itself, fs is integrate 0 to infinity e minus st ft dt. Now if you look at the integrand of those, we have e minus st ft. Then of course for the case of s positive, so we still have e minus st ft. So we have those integral e minus st ft dt. This absolutely converges. But for s negative, so what will happen is that e minus st ft dt, so if you consider s is negative, let's say s equal to some negative number u, say, right? So what happened, we have 0 to infinity e ut ft dt. Yeah, of course in this case this integral diverge. So we can see from there, s positive, that give you the integral absolutely convergence, and for s negative our integral diverge. So basically we have s equal to 0, it's separate between converge and diverge. So in this case we have sigma s is equal to 0, and for the order of convergence, exponential order, so which means this is our alpha. So therefore we have using the inequality that we have presented earlier, we have sigma s less than sigma c less than sigma alpha and less than alpha. And since sigma s is 0 and alpha is 0, so what we have is that this is 0, right? This is 0. So what we have is actually sigma c, the associate of convergence is equal to sigma alpha. This is equal to 0 as well. So we obtain the associate of convergence for that function, as well as the order of convergence for ft equal to 1. Alright, so other formulas that we might have usually seen, but I would prefer you to try to find or try to show that this is correct. For example, we want to transform E minus ZT ft Dutch function. Okay, so if we use the Laplace transform for this, so what we have here is this is integrate 0 to 0 to infinity. So we have E minus st, and then our function is that E minus zt ft dt. So this is easy to see that 0 to infinity here is minus s plus z t ft dt, and this is nothing more than the transform for the f of z plus s plus z. Yeah, or I can say this is the transform of s plus z. All right, and others you can see, like you can try to prove this. L fct s, this is equal to 1 over c f s over c. This is also not difficult to show. All right, and number 3 we have L h t minus t naught f t minus t naught. This is equal to E minus s t naught fs for t naught positive. Okay, so we have those t naught positive. So again, the way to prove this just almost similar to the first case. You just need to inspect the corresponding Laplace integral. All right, and also we have you can try this as an example. We can find L E minus ZT. Yeah. That will give you, according to that formula that we have here. So in this case, we have our ZT is 1. All right. So, and we know that the Laplace transform of 1. Yeah. We know that L1, this is 1 over s. So if our f e to minus zt, that will give you 1 over s plus z. So in this case, the singularity is at s minus z. Yeah, in this case, the singularity is at s equal to minus z. And this we call it as the damping function here. The damping function here. Save the singularity instead of in this case 1 over s. By adding that damping function, we has widened or make it the half plane of convergence larger, because we shift the singularity to the left of the original singularity as equal to 0. Yeah, by shifting that to the left means we make the convergence, the half plane of convergence larger. Okay, so and also from the formula we have cos t is equal to half e I t plus e minus I t, and sin t is half 1 over 2i e I t minus e minus I t. From here it is not difficult to show that L, this is not difficult to show that, so therefore I just write, therefore L cos t, this is 1 over 2 1 over s minus I plus 1 over s plus I, or you can write this as s over s squared plus 1. Right? And for L sin t, L sin t, this is 1 over 2i 1 over s minus I minus 1 over s plus I. So you can write this as a 1 over s squared plus s squared plus 1. So you can see for these two transform, these two functions, cos and sine, the singularities, the singularities occur at s plus minus 1, plus minus I, with you can see the abscissor of convergence phi s is equal to 0. I hope you can see this, why phi s, or the abscissor of convergence is 0, and the exponential order is 0. Yeah, exponential order of f is 0. So therefore the abscissor of convergence and absolute convergence are 0 as well. Okay, so that's the couple of example and also formula that it's not that difficult for you to look at, but it will give you, definitely will give you the more understanding on how to find the abscissor of convergence, how to find the order of exponential order of the function. Okay, and then the rest is just about the how to find the Laplace transform of the factorial function, how to transform powers and log, yeah, and also the we have transform of integral and transform of derivative, as well as we have a convolution. So I want you to study that in detail by yourself. Yeah, for the because it's just 10-13 minutes now, so let me give you some more topic here. The factorial function. The factorial function. Okay, so we define for fractional or even complex value of p, yeah, for fractional or complex value of some number p, say, then we define p factorial. Remember that p is fractional, yeah, the factorial of the fractional function, yeah. So p, we define p factorial by using p factorial is integrate from 0 to infinity e minus x to the p dx for real p greater than minus 1. So if you do integration by parts, I think you may take u, let's say u e minus x, yeah, I think du, you can take du e minus x dx, and you take v as a xp. So of course from that dv is a p x p minus 1. You can find u, this is minus e to minus x. Alright, then we can do by integration by parts. You can try couple of stages, and then you can generalize the whole terms. Yeah, so integration by parts, just doing that, integration by part. Will give us a p factorial. Remember that p is fractional or even complex. You can also use a p factorial as p minus 1 factorial. And of course for the positive integers, for any integers, positive integers, we know this n factorial, this is n minus 1 factorial, and also apply for the case of fraction. And it is obvious that when for 0 factorial this is 1, yeah, 0 factorial is 1, and 1 factorial is 0 factorial is 1, and 1 factorial is 1. Okay, so if we differentiate, yeah, the derivative of p, so we have if the derivative of p factorial in the half plane convergence, of course we consider the in the half plane convergence, in the half plane convergence, alright, so we have d p factorial dp. This is just integrate 0 to infinity, alright, e minus x xp ln x dx. Yeah, and at p equal to 0, so we have dp factorial over dp at p equal to 0. That gives you 0 to infinity e minus x ln x dx, and this actually will give you 0.5772 and so on. This we call it as a negative of a sigma, negative of a sigma, where so we call this as a Euler constant. Euler constant. Okay. Those recursive relation, the recursive relation is that we have earlier shows p factorial is p minus 1 factorial. So it shows that I can say I can write this using recursive relation. P factorial has a simple pole. Simple pole means the point where the function has singularity. Yeah. So simple pole at p equal to -1, -2, -3. Yeah? And in fact, all the negative integer. Now, in order to find the simple pole, to find the residue of the function and so on, so you need to expand using the Lorentz series. I think you can find out what Lorentz series is, that how to find the pole of the complex number. Just expand using the Lorentz series, and then you can find those points. Yeah. And then at p equal to half, so if we change a variable, let x equal to y squared. Yeah. So this change of variable give us, so what will happen, just substitute into those factorial. So we have -1/2 factorial. That will give us, this is equal to 0 to infinity. Alright, we have e minus y squared, because we take x equal to y squared, and xp, that give you, because p is minus half, so that give you 2 dy. Okay, so we have 0 to infinity to dy, and this always give you negative whatever y, because y is squared there, so you can consider this as a minus infinity to infinity e minus y squared dy, and this is nothing more than just surd of pi. Alright, so with those formula, the reflection of this factorial, we have p factorial minus p factorial. This give you p pi over sine p pi. But this probably we need a proof in the other parts. I don't know. I don't think we have enough time to look into that proof, and so I just skip the proof of those. Now, for this pole here, maybe I think I leave it to you as an exercise. Yeah, how to find or show that P has a simple pole at P equal to -1, -2, -3, and so on. Also evaluate its residue. Yeah, try this as an exercise. Show that P factorial has simple pole at point P equal to -1, -2, and so on, and we try to evaluate its residue at this point. Okay, so Yeah, as I mentioned earlier, I think you need Lawrence series. Write those things as a Lawrence series. Try to find the pole as well as evaluate the residue. Okay, so I think the rest is about transform of powers. You can read by yourself. Convolution. Convolution is as well. Of course, detailed note of the for the convolution. You can refer to my last semester video MTH 5. Forgot the code. Um, 51 MTH 50112 or 6012 differential equation, and the title of differential equation. So in this case, in this part, I give quite detail on the Laplace transform, Fourier transform, Mellin transform, and also the convolution of those. You can refer to any of those videos. So I think this will be my last video for this semester, for this subject. Hope you can cope with all the subject, all the topic that I have covered in this in the whole semester, and I hope you enjoy the study during your study. Either you're doing PhD or doing master. Good luck to you all. Bye bye.